Okay, we have talked earlier. I've talked about thermal noise. Now let's look at estimating thermal noise. In this example, we want to calculate the thermal noise voltage of a 100 kilo ohm resistor at room temperature, which is 290 degrees Kelvin, measured by an instrument with a 10 kilohertz bandwidth. If the resistor forms the input to an amplifier whose gain is 10 to the 5, that means 100,000. What is the noise voltage at the input and output of the amplifier? The answer is there, so you can work out for yourself. But if you want to know the solution, here's the solution. This is thermal noise. So the formula that's applicable is Vn squared equals to 4kTRB. So 4K is Boltzmann's constant, which is 1.38 times 10 to the power of minus 3 times T being temperature. Temperature we know is 290 degrees Kelvin, 290. Then we multiply by the resistance, 100 kilo ohm, so that's 100 kilo ohm. And then the bandwidth. What's the bandwidth? Bandwidth is 10 kilohertz. So since B is supposed to be measured in hertz, so that's 10 to the 4. So you have that number there. When you multiply all this out and you work it out, it turns out to be about 4 microvolt RMS. So the answer is 4 microvolt RMS for the noise voltage. And the thermal noise, after amplification, you just multiply that by the gain of the amplifier, which is 10 to the power of 5, and that works out to be 0.4 volt RMS. Okay. So minimizing inherent noise. So if you want to minimize the inherent noise or the device noise, then what we want to do is we want to minimize B, bandwidth B, because that's part of the formula. Then we want to keep the temperature low as possible, as practical. And we want to optimize the choice of input resistive components R. So if the input resistance, you can choose a low value, you use a low value, as low value as you can use. It's practical. And you want to minimize the input current at the first stage amplification, because that will add to the short noise. Okay. So noise and bandwidth. Let's consider this example here. We have two amplifiers. The question here is, which of the two amplifiers will produce lower thermal noise? Is it a 200 Hz bandwidth amplifier centered around 600 Hz, which is slightly on the low frequency side, or 200 Hz bandwidth amplifier centered on the 1 kHz, which is the higher frequency side? What do you think the answer is? Answer? If you look at the formula, Vn squared equals to 4kTRB, there is no center frequency element in this equation, so it really doesn't matter. As long as the bandwidths are the same, the thermal noise generated by both these amplifiers will be the same, even though the frequency band they are operating at different frequencies, but the bandwidth is the same, so it will be, the noise that it sees will be the same. So noise reduction strategies. Noise is a serious problem for the designer because noise interferes in the accuracy of your measurement. So the following is a common sense approach to minimize the effects of noise. Number one, you minimize inherent noise. So you know what inherent noise is, and you know how to lower the inherent noise, and you do that by reducing the source resistance and the input resistances that you use for the first stage amplifier. And then you reduce the bandwidth of the amplifier. Then you reduce the operating temperature, so you keep your circuit cool, don't let it get hot like in the hot sun or there's a hot device around. You minimize the input current at the first stage amplification, that will reduce your short noise. So that's, and you use a low noise amplifier at the first stage of amplification. And for external noise, what can you do about it to minimize? You use appropriate grounding, shielding, filtering to prevent external noise, and we will learn more of this in later chapters. And you use the lowest DC power supply voltage that will do the job. And if necessary, you use additional filters like band reject filters. If noise appears in your at a particular frequency band within your signal bandwidth, then you use a band reject filter to remove that portion out. This will introduce some distortion to your signal, unfortunately. But if the interference is bad enough, it's still a better trade-off than allowing the noise to remain in that signal bandwidth. So noise reduction by filtering. This is a practical way to reduce noise through limiting the bandwidth. And you can reduce noise, environmental noise such as power line, radio transmission. Example, you have an ECG amplifier. A low-pass filter can be used to eliminate the effect of high-frequency noise, which will help to prevent aliasing effect. For instance, ECG signal has frequency components up to 100 Hz. But if your interest is only at 35 Hz, then you can limit it to 35 Hz. Or if you want to just monitor the ECG, you're not doing diagnosis, 50 Hz, you can actually get away with 50 Hz. And then you will find that there's a reduction in noise, and your signal becomes cleaner. You can use a high-pass filter to eliminate slow motion artifacts. In ECG recording, you find that the ECG does not remain still. That means as it's beating, it might drift high and it might drift low. And if you want to remove this drift, you can use a high-pass filter which will remove all the low-frequency components, and then your signal now becomes beating about a ground level, okay, at a constant level. You can use a notch filter. A notch filter is a sharp, a very narrow band reject filter, and you can use that to remove 50 Hz noise. Unfortunately, the 50 Hz component will also be 50 Hz component of the ECG will also be removed. So this will distort your ECG a little. So it is best not to use this if you can avoid it. So computer assisted noise reduction. So once you digitize it, you now have other options. For instance, signal averaging. In signal averaging, what you do is you detect one cycle of the signal, and typically it's a periodic signal. At least in biosignals, it tends to be periodic. And if it is periodic enough, and you can find a point, let's say the maximum point of the signal, like the ECG QRS complex, and you were to align the signal there, by averaging the same signal over and over again. So sample for sample, you just add on and you average it. You find that the signal becomes clearer, so the signal that was very noisy will now tend to be cleaner, and the noise level drops at the rate of square root of n, where n is the sample number. So if you sample, if you do the averaging of 9 samples, then the square root of 9 is 3, so your noise level drops down 3 times. Smoothing. You can also do a technique called smoothing, which we will talk about in a short while. And you can use digital signal processing, where you use the power of computing to remove using some mathematical equation, which can either be simple or complex equations. So let's take a look at smoothing. In smoothing, you take a look at the original signal, which is in purple here, and you see that it's rather noisy. And if you do a 3-point smoothing, then what you are doing is you sum up the 3 signals, then you average it, and you find the average point, and you plot a point here. And then you do the next 3, so that's a moving average, and you do another point here. And then you do the same one, you get another point here. So now you find that the yellow points here, which are the average values, they tend to plot a smoother signal than the original signal. Whereas the original signal are moving up and down a lot, the average signal is rather smooth. So this method is called smoothing.